Okay, finally, let's talk a little bit about the exact analytic solutions to these problems here. We just spent some time, showing how to do this stuff graphically with a Smith chart and think about it in terms of these traversals here. But sooner or later, it's going to be really nice to just plug something into MATLAB and get exact solutions. So the book has a simple derivation, and it's exactly like we did last time, where you had these reactive elements and you just added the series plus the parallel bits. You equate the real to the imaginary, and you set the real part to the characteristic impedance, and then the imaginary part has to go to 0. Then you have to solve for the various lengths and reactances accordingly. So as you can imagine, it gets a little nasty because you have that characteristic, actually let's go back here. Remember, you have the input impedance looking down a length of transmission line now, rather than a simple reactance calculation for an inductor or capacitor. But overall, the derivation is the same. And I thought about doing it, but honestly, it's not the most instructive thing in the world. It's just a giant pile of gobbledygook and algebra. The main important thing here at the end of the day is all you need to know is there's an equivalent impedance looking down these two lengths of transmission line. And I'm just adding these two guys in parallel here, or series for the series line naturally. And I just want to equate the real part to this real transmission line impedance, and I want the imaginary part to go to 0. And that's fundamentally all this derivation does. So as long as you kind of understand that, you don't necessarily have to slog through all the steps on your own. All you need to do is be able to grasp what's going on and interpret the results and put it into something like MATLAB so that it will generate an exact solution for you numerically. Okay, so that's the derivation here for the shunt stub, and then you just do the same thing for the series stub, and you notice they equate the admittance, and then they add things together. You get a real and a reactance, and you get these very yucky equations here. Okay, but it's just basic algebra to get through these steps, and what's mostly important is, can you apply these equations to get exact results? Or if that's too much work and you don't want to code up some crazy function in MATLAB, then you can always use your Smith chart to do essentially the same thing. So this is where you get that idea of a Smith chart being essentially like an analog computer. Like all of the rules of the transmission line are built into the geometry of this thing. And they allow you to sidestep some of the extra nasty bits of these kinds of derivations. So I'm not necessarily going to force feed you this particular derivation. You should be able to follow it if you really tried. And I tried to do it, and it is like multiple pages worth of gobbledygook, and that's okay. So as long as you can follow the results and write your own MATLAB function that carries out these equations and gives you correct answers, then you know you've done a good job and you don't have to necessarily slog through the derivation yourself. Okay, so those are the closed form expressions for the shunt and the series and shunt stub transmission lines. And you can see how everything's normalized as well to wavelength. So obviously the results have to be interpreted in that sense. Given different frequencies, you'll have different distances, but the proportions relative to the wavelengths will be the same. Okay, so intuitively, again, think about this in terms of there's an equivalent impedance, a parallel impedance between these lines, but also remember what's physically happening is I have an initial signal comes here and it sees this impedance mismatch, which causes a reflection. And then that's going to propagate down, see this mismatch here, create another reflection, which will then bounce back again. And also there'll be an excitation down this line, which then bounces and comes back this way. And all of these things infinitely bounce back and forth into each other. And if everything is tuned just right, the net result is that all of the transmissions here contributing to this signal here will destructively interfere with the initial reflection, say. And the end result is you get no reflection because everything is destructively interfering that way, and you get perfect constructive interference and delivery to the load. So that is the basic idea of what will physically happen inside this stub. So it will work at a continuous frequency, but there will be this kind of transient mismatch as signals bounce back and forth here. So kind of keep that in mind as well if you're sending, say, little short band limited pulses or high frequency information through these things. There's definitely a band limitation to this kind of system. Okay, so that is pretty much everything you need to know about series and shunt stub matching, and we'll do lots of examples in class, and you'll also do this on one of your labs to help reinforce a lot of the applications for yourselves.